The orbitals are written out in this little picture right here. And you can see, first of all, that on the far left side, we see s orbitals, which are basically spheres. The bottom one is 1s, and that's smaller than 2s. And 2s is smaller than 3s. So the n value, which is n equals 1, n equals 2, n equals 3, as the n gets bigger, the orbital gets bigger. So 2s is bigger than 1s, 3s is bigger than 2s, etc., etc. But before we do the other ones, we should talk about what the letters here are, because here we're seeing n and l together. So this is called NL notation, and we're going to see that both N and L are important when you want to figure out the energy of where the electrons are. Now, if you used, for example, in 1s, S means L equals 0. Stupid there on the left-hand side. Anyway, L equals 0 means S. So 1s, if you used N and L together, it would look like 1 and 0 or 10. And it's hard to know if you had 10 or 1 and 0. So that's why scientists use NL. They use a letter for L so that you know right away that N equals 1 and L equals 0. So if you have, for example, 3p, n equals 3, because 3 is the n value, and p means L equals 1. So for 3p, you would have n equals 3, L equals 1, etc., etc. And that's why they use it. Now, for 1s, 2s, and 3s, there's only one orbital, because L equals 0, m sub L equals 0, one value, one orbital. But when you get to L equals 1, which is p, then you have m sub L minus L to positive L, m sub L minus 1, 0, plus 1, 3 values. So that's when you start to see the orientation effects. So when you have L equals 1, the p orbitals, you're always going to have an x, a y, and a z. That's why they say 2px, 2py, 2pz, and then the bigger versions above, 3px, 3py, 3pz. Pretty cool. When you get to d's, L equals 2, then you start to have m sub L minus 2 to positive 2. That's minus 2, minus 1, 0, plus 1, plus 2. 5 allowed d values. So you start seeing 5 of them, and the orientations get a little bit more complicated, but you just have to realize there's 5 different versions, 5 different orbitals when you get to the L equals 2, i.e. d subshell. So it's pretty cool. So this is why they use NL notation. All right, both the number for N and really the number for L are important for energy, but you can't put the numbers together. It might be confusing. So that's why people use letters for L. Kind of cool. So here's an orbital. We have n equals 3, L equals 1, m sub L equals minus 1. The question is, what type of orbital is this? So we'll use the NL notation. So the number will start with 3 because that's what n equals 3 is. And L equals 1 means it's a p subshell. So we would call this a 3p subshell. All right. 4d would be n equals 4, L equals 2. 3s would be n equals 3, L equals 0. 3d would be n equals 3, L equals 2. So you can start to see what it is. You don't need to know which of the orbitals it is. You just need to know it's one of those types of orbitals in the 3D set. Like you don't know if it's 3D z squared or 3D xy, or in terms of 3p, you don't know if it's 3px or 3py, but you at least know it's 3p, and that's cool. Nodes are places where the wave doesn't exist. And we saw in standing waves, there were places where the wave went up and down, and right in the middle was a node. There were no density. Well, it's important to know that there are 2 types of nodes when it comes to orbitals that are really important. And why they're important is because electrons are kind of the glue that holds molecules together. And if there's no electrons there, there's no glue to hold anything together. So nodes are places where electrons aren't present and you can't make a bond there. So there's 2 types of nodes. One is called spherical or radial nodes, and to figure it out, you just go n minus L minus 1. So let's look in the upper right hand corner. That is a 1s orbital. So n equals 1. S means L equals 0. So in this case, there would be n minus L minus 1, 1 minus 0 minus 1, 0 radial nodes. But when you go to the lower one, when you go to 2s, now n equals 2, L still equals 0. 2 minus 0 minus 1, 1 radial node. And you can see in the middle there, there's kind of like a white sphere. That's the node. It's an area where you can't have any electron density, so you won't have any bonds form right there. And you can keep going 3s and stuff like that. Now, another kind of node is called a planar node, and a planar node is like a sheet of glass that separates the different parts of the nodes, and the planar nodes just equal L. So for an S node, there are no planar nodes, but when you get to P, which is L equals 1, then you're going to have one planar node. This is one of those figure eights I talked about, and this right there shows the node. There's an area between the left and the right parts of the figure eight where there's no electron density, so you're not going to make any bonds right there. Likewise, D means L equals 2, so you'll have two sheets of glass kind of separating those parts out. L equals 3, 3 planar nodes, etc. like that. So again, nodes are just important because there's no electron density to make bonds. That can be important when you get to certain types of concepts when making molecules. Let's just go through some examples of types of orbitals. We'll look at some s orbitals. On the left-hand side is a 1s orbital, and you can see it's pretty small. It has 0 radial or spherical nodes and 0 planar nodes, not too much happening. If you go to the bigger 2s, though, then you can see right away it is, first of all, a bigger a bigger orbital, I should say. It's bigger than the 1s. This has, though, one spherical node. And if you look at this picture on the right, if you look very carefully, there's kind of like a white circle that goes around. That's the spherical node. It's actually an area where you can't make any electron density. In the upper graph, you can see it right there. That's the spherical node. That's like a slice of the spherical node right there. Anyway, just realize there's one radial node. If you go to the bigger 3s, then you even have 2 spherical nodes, and you can see them both in that diagram. Now, that kind of mesmerizing picture in the upper right-hand corner is trying to show you then the spherical nodes. And you can see there's like circles within circles. The circles can represent the spherical nodes where there's no electron boundaries happening. P orbitals are somewhat similar. So on the left-hand side there's a 2p orbital. It's 2px technically. We don't have to worry about that. Now 2px has 0 spherical nodes, but because p means L equals 1, you will have a planar node. So you can see in the middle there's no electron density happening. That's where the nucleus is in this case, which is kind of cool. If you go to the bigger 3px, then you do, first of all, have a bigger orbital because 3 is bigger than 2. You still have the planar node, but now you actually have a spherical node. So there's more complicated types of areas with no electron density as the orbitals get bigger. But again, all of these more or less look like a figure 8. Some of them are funkier than others, definitely, but that's kind of the idea. So the question here is how many total nodes are in a 4p orbital? Now, 4p means n equals 4. That's what the 4 means. And SPDF, P, means L equals 1. So the number of planar nodes equals L. There's going to be one planar node. And spherical nodes, or radial nodes as they call them in this book, n minus L minus 1. So for this 4p, that would be 4 minus 1 minus 1, 2 radial or spherical nodes. So if you have one planar and 2 radial or spherical nodes, you're going to have a total of 3 nodes in the 4p orbital. So again, to figure questions like this out, you have to calculate both planar and radial or spherical. In this case, it's 1 planar, 2 radial, so for a total of 3 nodes. The Ds are pretty cool looking. Ds we're going to see are the domain of transition metals, which are one of my favorite. And you can figure out radial and spherical and all that kind of stuff. Now, most of the Ds look like 2 figure 8s together. And if you look at 4 of the 5 of them there, that's kind of what they are. It's like 2 figure 8s kind of squished together. And they're on different axes, all that kind of jazz. But check out the 3D Z-squared orbital in the kind of middle lower part there. I call that the donut orbital. It's like one figure 8 with a donut around it. And again, the math is just crazy how they figured that out, but it is cool. That's always the one kind of weird orbital in these. So again, just remember that when you have a d orbital, that means L equals 2. And m sub L goes from minus L to plus L, which would be minus 2 to positive 2, minus 2, minus 1, 0, plus 1, plus 2, 5 d orbitals. And this is what we're seeing here. So each of those has a different m sub L value. That's why there's 5 of them. They're kind of cool to look at. Which orbital would you expect to have the most volume? All right. Now, volume, of course, is three-dimensional space, and you've seen many different kinds of orbitals here. But the important part is that as n gets bigger, the orbital itself gets bigger. So more than the SPDF, I would just predict that the 4 in 4F would have the most volume. F has a lot of volume as well. We'll see some pictures of those here in a little bit. But the biggest thing is that n is proportional to the size, and as n gets bigger, the volume gets bigger. Probably the 4F would have the biggest volume. The F orbitals, there's 7 of them, and they get even more interesting. So on the right-hand side there, you see the 7 F orbitals, and more or less, they're kind of like 3 or so figure 8s put together, but you do start seeing some donuts. So in the top one there, the FZ3 thing there, you begin to see like 2 donuts inside. So you're seeing the progression here of the different orbitals. At the top on the left-hand side, this is an S orbital. The second row down, if you will, this is the P set. So you have PX, PY, PZ. The next set down is the D set, which are ones we saw in the previous slide. And then these 2 right here would represent the Fs. But notice the patterns. You've got 1 orbital in S, 3 orbitals in P, 5 in D, 7 in F, etc., etc. Quantum mechanics is filled with patterns. This is one of the patterns you can check out. Let's do an example where we want to figure out the different quantum numbers for the n equals 3 shell, okay? So we're starting with n equals 3, and we want to find L, the subshell letters, the NL notation, the m sub L values, and the number of orbitals. And this will be a good idea to show the different things we've talked about so far. So first of all, when n equals 3, L values go from 0 up to n minus 1. So 3 minus 1 means it's going to go up to 2. So L always starts at 0. It's going to go up to 2. There's going to be L values of 0, 1, and 2. L and n can never be the same thing, but they will be up to n minus 1. And notice that means 3 L values here for n equals 3. Now the letters that go along with this is where you do the SPDF notation. L equals 0 is S, L equals 1 is P, L equals 2 is D, etc., etc. So instead of talking about L equals 0, scientists will usually say the S subshell or something like that. So the NL notation will be the number 3, because this is the n equals 3 shell in front of those letters. So 3S would be the first one, 3P would be the second one, and 3D would be the third one. So you can see how this stuff begins to fall in place. You could have, for example, a 4S, 4P, and 4D. So this is a way to distinguish between the two of them. M sub L values depend on L. M sub L values go from minus L to positive L. 0 is always going to be a value. So for 0, that just means M sub L is going to be also equal to 0, because minus 0 to positive 0 is just 0. But when you get to L equals 1, then you have M sub L minus 1 to positive 1. So that would be minus 1, 0, plus 1. There'd be 3 M sub L values for that. And when you get to L equals 2, minus 2 to positive 2, you can see there's 5 different M sub L values that are possible. So because there's 1 M sub L value, that's why there's 1 orbital. Because there's 3 M sub L values when L equals 1, that's why there's 3 orbitals. 5 for the D, etc., etc., which is what we saw in that last slide. And then the number of orbitals literally equals the number of allowed m sub l values. And remember, m sub l equals 0 is an allowed value, just like all the other ones. So for the first one, there would be one orbital, because m sub l equals 0 is allowed. For the second one, we have -1, 0, +1. Those are 3 allowed values, 3 orbitals. 5 for the last one, etc., etc. Now, if you're starting with n and you want to know the total number of orbitals, you can just go n squared. So 3 squared will get you 5 plus 3 plus 1, or 9, all right? And that's kind of a quick and dirty way to do these kind of things. Quantum mechanics is filled with little expressions like that. Some people like them, some people don't. It's just one I wanted to tune you into. Some people prefer the train track model when thinking about quantum numbers, which is fantastic. We just looked at the n equals 3 example right there. And n equals 3 broke down into L values of 0, 1, and 2. So when L equals 0, there was only one m sub L value, one orbital. But when L equals 1, there were 3 m sub L values, or 3 orbitals. And when L equals 2, there were 5 m sub L values, or 5 orbitals. And you can do the same thing for 2 and 1 and stuff like that. So whichever method you use, it's important stuff to figure out. And again, it's not too hard. And again, what's kind of cool is this is all the results of some pretty high-level math, and they were able to do it. Pretty awesome.